Okay, so welcome everybody. Yes, welcome everybody. It is my pleasure to start this new session of the DISAT seminar, which is about, broadly speaking, probability and statistical mechanics. Today we have the pleasure to host Anna Paola Muntoni from Polytechnic di Torino. She will speak about an approximate solution to the compressed sensing problem. Please, Anna Paola, go ahead.
Okay, hello everybody. As Matteo told us, my name is Anna Paola Muntoni, and I work as an assistant professor at the department DISAT in Polytechnic di Torino. And I really thank you for this invitation. I'm so happy to present this this part of my work that I started during my PhD. And I had a few opportunities to speak about this. So I'm very happy to share with you all the results that we achieved during these years. So I didn't prepare many slides because I really love to do it, to present slowly and to give you all the details step by step. So you know the audience is very broad, and if you have any question, you can. I will be very happy to take them during the seminar and to discuss with you during the slides. So let's start. My topic for today is the compressed sensing problem, and I will say to you how to face this using some tools that have been developed in the field of statistical mechanics. In particular, this approximation technique that I've been explained, I will explain to you. It's called expectation propagation. So okay, let's start. How can we explain the compressed sensing problem? So in general, we want to solve a system of linear equations that is ill-posed, meaning that the number of equations that we have is smaller than the number of elements of the solution that we want to retrieve. And the machine, if you want to see the compressed sensing problem as let's say an inverse problem, we can think of a signal in general X that go through a machine, let's say a sensing machine, that is characterized by a matrix A. This machine perform a certain number of measurement, and this number of measurement is m, and this m is smaller than n, so the size of the original signal. This machine A produces an output. This output is stored in a vector that is called y. So in this formalism, we called y the measurement vector. Instead, A is the sensing matrix, and X is the signal that we want to recover. So since these numbers are all, let's say, real numbers, there are, let's say, a way of designing this sensing matrix A such that the vector Y will be as informative as possible. But in general, in general settings, this problem is ill-posed, as the number of solutions that we can provide for this original signal X is in principle infinite from the pure mathematical point of view. So how can we retrieve the exact signal knowing, let's say, the compressed version of the signal, which is the measurement vector Y, and the matrix A? So to give you an idea of a set of applications that are linked to the compressed sensing problem, I have chose two examples. One is let's say, an historical one, and is the problem of image compression. So in image compression, what you want to achieve is to, let's say, store a picture that is in principle made of megapixels. So you have to store in your computer order of 10 to the 6 at least numbers, which are the intensities of each pixel in these, let's say, black and white images. And instead of storing all these numbers, you want to store a compressed version of it. So a number of variables, let's say a certain numbers of pixels of other, let's say, auxiliary variables that are, let's say, quite less in numbers. So the idea in these image compression settings is that you start from the original image, you perform a kind of transformation. For instance, in literature, you see example when you use, for instance, the Fourier transform or the wavelet transform. For instance, in this case, we use the wavelet transformation, and this is basically a linear transformation of the image, and the coefficient that you get are of the same number of the original pixel in general. Then what you do is to zero all the coefficients that are, let's say, smaller than a threshold that you decide a priori, and you only store the largest ones. From the largest ones, let's say you invert the relationship between the coefficients and the image, okay, and you retrieve the original signal that in this case is the image that you want to compress. So here in this particular example, the image contains, let's say, 10 to the 6 intensities, and the number of coefficients that are stored during the compression is 20,000. And you see in the panel C that basically you have no error here. So the image is completely recovered from, let's say, a number of coefficients that is quite less with respect to the original number of intensities. So this is, let's say, a very historical example. This picture is actually being taken from this paper that is the seminal paper for understanding the compressed sensing problem, in my opinion. A very recent, let's say, application of compressed sensing that I have discovered basically in this year or last year is about the pool testing problem that has been rediscovered basically during the pandemics. So this pool testing problem is also known as the Dorfman method, and consists in try to test, let's say, individuals, let's say n individuals, but by exploiting a number of tests that is smaller than the number of individuals that you want to test. It's in a way is a way of performing collectively a certain number of tests that may be expensive for some reason, and to get, let's say, the same results as you could have done by exploiting the maximum number of tests that in this case is n, the number of individuals. So how it works in general? So that let's say the first research that let's say invented this idea thought of it about in this sense. So he assumed that the number of let's say tested positive individual will be much smaller with respect than the number of individual to start with, so n. And he decided to split, to create subgroups that are called pool, where basically they collect the biological sample of each individual in a collective biological sample. So for instance, these n individuals are all divided into 6 groups, okay? And then the tests are only performed for each pool, okay, in this collective, let's say, sample. So you see that the number of people is n, the number of tests that are performed in this first round is only 6. Then only one pool will be tested positive, so the red one, this one, and then in the second round of tests, they perform individually the tests of it to each individual. So now the total number of tests here is 6 plus 9, the number of individual in the first tested, in the unique, let's say, positive pool. So this is the basic idea, and it is valid if the number of people that are actually infectious is much lower than the number of individuals in general. And the problem of this, let's say, original testing procedure is that you have 2 rounds, and in a sense, from the point of view of human resources, it could be very, very, very slow. Okay, because it takes time to have the results of this test. So the idea instead is to use some knowledge that this PCR test in the case of COVID-19 is available to us. So when you perform a PCR test, what you measure is basically the fluorescence of the biological sample that you have collected. And this fluorescence depends on the number of PCR cycles. So how it works, basically, the RNA that is present in the sample is amplified during this cycle number. So they say the number of DNA copies is amplified during this time. And if the fluorescence of the sample is larger than a certain threshold, that in this case is the horizontal line means that the sample is tested positive. Okay, but depending on the number of the PCR cycle where this let's say threshold this threshold is overcome, and let's say in the region of this space where the point, let's say your test line lies, basically if it matches one of these colored curves, you can recover also, let's say, the number of copies of DNA in the original, so in the initial sample. It means that when you perform a PCR test, not only you know whether a sample is positive or negative, but you also know what is the viral load of each sample. Okay, so how much, let's say, RNA, how much viruses are present in the sample. And this idea can be exploited to solve, let's say, the original problem as a compressed sensing problem, because now we can say that this measurement vector y contain in each entry I, the viral load that has been measured by the test. And this sensing matrix for us is a sort of participation score that is equal to 1 if the sample of individual j participates to the pool I, because each individual can participate to many pools concurrently at the same time. And xj is the viral load which is associated with each individual j. And this xj is actually what we want to know, whether this viral load of each individual is larger than a certain threshold. So if this the individual j is negative or positive. Okay, so this is a really recent application of a compressed sensing problem that in these days is kind of popular because of COVID-19 spreading. But okay, let's come back, let's say, to the formalism of this problem and how to address this problem. So we say that so from the image reconstruction, we don't have to assume any, let's say, any form of the variable x, but what we use is kind of an assumption about the gradient of the image. So we say that the neighboring pixels should be very close in intensity, as what we do is to try to, let's say, minimize a certain gradient of the image. But in general, what we assume is that the signal that we want to reconstruct is sparse. In the case of pool testing, we want that the number of individuals that are actually infectious is much smaller than the number of individuals in general. And what we can say mathematically is that since the signal x is sparse, it means that only a fraction of the components is non-zero. So among all the n elements that form the original signal x, only k of them are non-zeros. So as, let's say, the original picture that I show you. So here, among all these elements of X, only 3 of them are, let's say, in gray. The other one are all white. Okay. Then we can also address, let's say, the either the noiseless case, so where this system of linear equation is perfectly satisfied, or in the noisy case. In both cases where you have, let's say, additive noise, so you said your true vector of measurement y that can be affected by some noise w, or also multiplicative noise. So you have your true, let's say, measurement vector y, and you multiply, let's say, component wise to an errors, to a noise w, and this w is assumed to be known, let's say, by distribution. So you know that this noise depends on the machine, and they follow a certain probability density. In general, what we assume is that this noise is Gaussian, as we will see in a second. Okay, so you can map originally this problem as a constraint optimization problem. So you want to find, of course, in the noiseless case, you want to find the original signal X such that it satisfies the linear constraints given by the sensing machine, and it also minimizes a certain, say, regularization. And this regularization accounts for the sparsity of the signal. We have several choices. Let's say the most popular one, I think, is the L1 regularization, when you want to minimize the sum of the absolute value of the signal, okay? And of course, the strength of this minimization will be governed by this lambda 1, which is, if you want, a Lagrange multiplier, or let's say a strength of this minimization. Another one is the L2 regularization, and say the more strict regularization is the L0, where you impose that exactly n times y minus rho, so basically n minus k of the original elements of the signal are equal to 0. So you want a solution that matches perfectly with the sparsity of the signal. But you can see, so the green one are very easy because they lead to a convex optimization problem. Instead, due to the form of this f function here associated with the L0 regularization, dealing with the L0 case is very hard, and you have to use some approximation. First of all, so before going into the details of the approximation that I've been using, I want to answer this question. So I want to know how hard it is to find a solution for this kind of problem. So let us consider at the beginning the noiseless case, and let's say the thermodynamic limit, where the number of elements of the signal going to infinity, as well as the number of equations, but we have a fixed, let's say, ratio m divided by n alpha rate, which is basically how much information I have from the sensing matrix about the signal. Well, if, let's say, the number of equations that I have in the sensing matrix is larger or equal than the number of non-zero of the X signal, what I can do is to, let's say, try all the n choose k possibility for the non-zeros value of X. So select the columns of A that are associated with my choices and try to solve the reduced system of linear equation that in this case will be solvable, because I have let's say a number of equations that is larger or equal than a number of let's say of the size of the system. So my system of equation here will be either solvable, or let's say I will have an over determined system of linear equation, because I have more equations than the number of unknowns. But unfortunately, in this regime, the number of possible choices that I have to try is scales exponentially with the system size, so the number of elements of X, and so it's computationally intractable. Instead, if I have a few equations, so the number of equations is smaller than the number of unknowns, I have not enough information to solve this problem, and so the problem is hard, and it's impossible to solve it in this thermodynamic limit. Knowing this, I say, a priori knowledge of the solution space, let's say, what people have tried to compute where the perfect line reconstruction, where you assume, let's say, the L0. So when you try to do this argument here, or when you try to impose a L1 or L2 regularization. So here, rho, as we have said before, is the fraction between the number of non-zeros entry in X divided by N. Instead, alpha in the y-axis is the number of equations divided by N. And so this C here means critical, because you have some sort of phase separation between a solvable problem and an unfeasible problem. So the gray area represents the cases in which the problem cannot be solved, because the number of equation A is smaller than the number of non-zero entries of the signal. So for, let's say, a certain number of M, which is above K, it's in principle, so all this white area here is in principle feasible to retrieve a solution, but it is very hard. In particular, if you use an L1 regularization, you will get a perfect reconstruction only for value of alpha that lies in these red lines. So there is a region between L0 regularization and L1 regularization where this reconstruction is in principle doable, but it's very hard. And if you use L1 regularization, you will get a perfect reconstruction only in this line, which do not coincide to the blue one. Okay, so this region is the more interesting, let's say, from an algorithmic point of view. If your algorithm is able to retrieve a solution in this regime, or I mean, the closer it gets to the L0 line, the better it is. If you use L2 regularization, basically you need a number of equations to get perfect reconstruction here that is equal to the number of entries of X. So basically you can only retrieve perfect reconstruction if you have a number of equations that is exactly equal to the number of unknowns. And so basically you are able to invert the matrix in the beginning to begin with, and then to get, let's say, the original signal in the noiseless regime. Okay, so you can find all this discussion in these two papers. One made, let's say, from a more mathematical point of view, and it's been written by Dono in 2006. And another one instead exploited message passing and also some replica trick calculation, and it's been published in 2009 by Kawashima. Okay, so what we developed instead is a way of, let's say, solve the comprehensive problem for single instances. So we have a machine that provides some measurement, and we want to ask in the finite case, so for fixed n, fixed m, how can we find the best possible solution, x, given that we have the measurement vector, the sensing matrix, and we also assume an L0 regularization for the signal. And we exploit what is called the Bayes theorem. So we want to investigate what is the a posteriori distribution of the signal x given the measurement vector y. And this is equal to the probability of y given x. This let's say green probability is called in the Bayesian framework is called the likelihood function of the data, in this case y, times the probability of x. This red probability is called in this framework a prior probability of the signal x, all divided by the probability of y. This probability of y is called the evidence, and it encodes, let's say, how we trust, let's say, our measurement. We can put some error in the measurement if you want, but in general, since this probability does not depend on the unknown x, is often neglected. So we will focus on the a posteriori probability p of x given y, which is only proportional to the likelihood function times the prior over the x. So in our case, the likelihood only enforces, let's say, the linear constraints, because we want that this x will be such that the product A times x will give, let's say, the measurement vector y. And how can we impose these hard constraints? So either we can exploit a delta Dirac function, or we can, let's say, write it as an exponential. So in this, let's say, Boltzmann-like fashion, where we have introduced a beta parameter here. So if beta is going to infinity here, all the distribution will be concentrated around the value of x that, let's say, perfectly matches y when multiplied by a. Instead, for finite beta, we can actually map the additive noise case, because here, when you compute, let's say, this difference, you will get the error w. And so since this w is distributed according to, for instance, a normal distribution, this beta here is the inverse variance of the noise in the noisy case. But we did, let's say, simulation in both cases. What about instead the prior? So the prior here has to model the sparsity of the signal, and we can, let's say, this formalized is very general, and you can see that can cope with both the L2. It's not written, but you can imagine that. I mean, it can also be written as a product of univariate Gaussian in the L2 regularization case. Here we have the L1 regularization, so we can say that this single prior function is a Laplace distribution, okay, and or the so-called Spike-and-Slab prior that enforces the L0 regularization. So here we are saying that with probability 1 minus rho, we have 0, and with probability rho, this xi is distributed according to a normal distribution of variance lambda 0 and mean 0. Okay, you see that this prior is factorized over the variables, and this is correct because as in the constraint optimization problem that I've shown you before, these penalties, if you want, are factorizes, and so also the probabilities, if you want, factorizes. All variables in this sense are independent from one another. So in general, so if we are able to know a posteriori distribution of the x given the y, we can estimate, let's say, the true signal x by maximizing the a posteriori distribution. So in general, we should perform this maximization step. Or it can be proven that actually it is better for an estimator to first compute, let's say, the marginal probability of the xi variable from the conditional distribution, and then to compute the expectation value computed from the marginal probability. And so this is actually the best estimated that you can get from in the Bayesian framework, and is actually the one that we will try to get. Unfortunately, in these settings, the problem in both cases, so either if you want to compute this or you want to compute this, the problem is hard to compute. So the two estimators are hard to compute. It's actually impossible to do that because here you have to maximize something, so you have to compute the normalization of this distribution that it's not feasible, and it is not feasible. Here you have to marginalize something that cannot be normalized. So in general, you cannot compute this. And the problem of this computation arises from the functional form of this prior, because this is, let's say, B model. Is a product of B-model distribution, and you can think of, I mean, if you try to compute all these integrals, you see that it's not possible to do that in general. Instead, the L1 regularization is doable. So what we want to treat is instead the L0 regularization case, and we address it using approximation. The approximation, sorry, that I want to use is called expectation propagation, and it's been developed originally in the field of machine learning by Minka, and in the field of statistical physics by Manfred Hopper and Winter in 2005. And it consists in approximation, say, an intractable distribution P into a feasible distribution Q, and this Q in general belongs to the exponential family of distribution. In this case, it will be a multivariate Gaussian distribution, and we will see in a second. There are a lot of applications of these techniques and a lot of problems. So this is a small list, but here you can see a website where these initial, let's say, applications are all stored and collected if you are curious to and you want to look at it. But let's say that in general, what I can say is that okay, the approximation that we will try to introduce here is Gaussian. So this Q will be a multivariate Gaussian distribution, and of course it will be exact if the original variables, so in this case the X signal that you want to retrieve, is distributed according to a Gaussian distribution. It is a, let's say, it goes behind the naive mean field approximation that we studied in general in statistical mechanics, and also belief propagation or message passing techniques for continuous variable, which is called, let's say, GABP, or also approximate message passing. And because it is able to cope with very correlated variable, instead this mean field and belief propagation, they need to assume that the variables of interest are lightly correlated or not correlated at all. Instead, these techniques is very powerful in this sense. So for what concerns me, let's say I applied these techniques to a lot of frameworks. So compressed sensing, as we will see in a second, but there are also the works where this method is being applied to the inference of metabolic fluxing, the reconstruction of tomographic images, so on and so forth. And I want to mention that if instead you want to deal with discrete variables instead of continuous variables, there is, let's say, a new version of it that's been developed by some people of my lab, and the density consistency approximation has been applied to statistical physics model in particular to spin models, and I also participated in the Ising inverse problem solution using these techniques. So in general, it is very, very powerful, and I will give you, let's say, the details how it works now. So our goal in the end is to try to estimate an approximation of the marginal probability of this a posteriori probability P of X given Y, where, let's say, the likelihood function has this form and the prior is factorized over the variables X. Let's say this likelihood function for us is kind of treatable, because this is, if you want, it's a Gaussian Boltzmann like, let's say, distribution. Instead, this one is a product of B-model densities. How can we represent, let's say, graphically this probability? What we use is a factor graph representation where I don't know if you're familiar with it, but very briefly, I can say to you that it's a way of representing, say, constraint variables. And in our case, we have, let's say, our true variables are the x1, and they will be represented as cycles here. And the link connects each variable to the constraints they are subjected to. For instance, this huge, let's say, square node in this graph represents the constraints imposed by the likelihood, where all these variables are coupled, okay, because the sensing matrix participate, I mean, in this matrix multiplication, all these components participate to give this final vector y. So this big factor basically couples everything together, I mean, or partial, or let's say a subset of them, depending on A in the end. Instead, these small square are, let's say, are acting one by one to a specific target, which is a specific variable. So each one will only have one of these small squares. And these small squares are associated with each of these factor in the prior, okay? The idea of, let's say, this Gaussian expectation propagation is to replace each exact prior, which is bimodal density, to a Gaussian, univariate Gaussian distribution of variance equal to bi and the mean value equal to ai for each I. So the factor graph that associated with the full approximation is the following, where we have kept, let's say, the likelihood function, the likelihood constraints, and we have replaced the gray square of the true exact prior with the approximated one. So now our Q has the following form, and you, let's say, collect all these terms, you realize that in the end, this Q is a multivariate Gaussian with a mean, say, value mu, and a covariance matrix sigma, big sigma. Now the problem is how can we get the value of these variances and the value of these means of the univariate Gaussian of the approximation. And to do this, I will do the following observation. Suppose that you have, let's say, the approximated multivariate normal distribution and the true one, this one, and you want to estimate the marginal probability of a specific variable xi. Of course, if you compute the marginal from this distribution will be very easy because you only have to marginalize a multivariate density. But you are missing something because here you are using, let's say, the approximate prior for the xi variable. Instead, what you can do is to basically you can start from the full approximate Gaussian. You can remove the approximate prior for the xi variable, and you can replace it with the true one. What you get in the end is the so-called tilted distribution, where you have the exact likelihood, the approximation of all the priors xj, but the I that you are, let's say, is your target, associated with the target, say, margin that you want to compute, and then you multiply it by the true prior here. So graphically, this is the factor graph that you have, where you have the exact likelihood. These are all the variables that you're interested in. These are the priors, all approximated, except the one associated with the ith variable. And of course, since, let's say, this priors is exact, you assume that you can get a better approximation of the marginal and expectation of this marginal if you do this replacement. And this idea is actually exploited during the learning of this A and this B. Why? Because now we can say that in order to find this A, unknown A and B, what I want is to minimize the Kullback-Leibler divergence between the tilted distribution that I've just defined and the full Gaussian approximation. So if I see, let's say, if I look at it from a graphical point of view, this is the factor graph associated with the multivariate Gaussian, and this is the factor graph associated with the tilde distribution. And what happens to the variable xi is that you have on one hand, you have this Gaussian part, it is called the cavity one, where you consider the statistics of everyone except the ith, multiplied by the approximated prior. Instead, here you have the same cavity part multiplied by the true prior. And if you compute formally, if you minimize, let's say, the Kullback-Leibler the Kullback-Leibler distance between the two densities with respect to the two parameters that you want to determine, so the bi and the ai, you find in the end that you have to match the first two moments of the two distribution. And this gives you the, say, an iterative scheme that at convergence will give you the value of the mean and the variances of the Gaussian of your approximation. So what you do is to start from a random set of mean values and variances, then you compute in a first step all the statistics for this tilted distribution, you match the moments, and by matching the moments, you get some equation for the new, let's say, so the A and the B at the next iteration. And you repeat it until you get some numerical convergence. Okay, so this is, let's say, the general scheme. And now I will show you some results associated with the compressed sensing problem. So what we did at the beginning was to apply this scheme for, let's say, a certain number of instances, and where the sensing matrix A is composed of IID Gaussian, let's say, entries, or uncorrelated, okay? And so here you have this phase diagram plot. So the white region is the region in which the algorithm did not converge, and you see that it matches perfectly with the unfeasible region. Then so this R is the Pearson correlation between the true signal and the signal that has been recovered by our technique. And if it is equal to 1, of course, you get the perfect reconstruction. Instead, if you go into orange or red, you get a Pearson that is, let's say, still positive, but is smaller than 1. So you have a reconstruction that is not perfect. And if you, let's say, compute it for many times, and for a fixed row, you use some kind of, bisection techniques to reach, let's say, the best alpha in which you get a perfect reconstruction. You see that this perfect reconstruction line algorithmically for expectation propagation lies between the L0 line and the L1 line that has been computed theoretically. So it means that for a fixed row, you can get perfect reconstruction using less equations than a L1 approximation, but still there is a gap, let's say, between the L0, where everything is in principle possible to solve, and our algorithmic line. But anyway, this is, let's say, a nice result. What I think is nicer is what happens when you have, let's say, correlated entries in this sensing matrix. And to do that, let's say, numerically, we compute these covariance matrices that are composed of, let's say, the product of S transpose S, where S is a low rank matrix, where the rank is equal to K. And of course, this D is diagonal, such that this covariance matrix C is in the end is a full rank. But you see that the fact that this matrix is computed, means is defined in this way, is giving you some correlation between the entries of the sensing matrix A. And you can see that, so we compare, let's say, our success against other techniques to solve the compressing problem. In particular, I want to stress that EMBP is belief propagation with an expectation maximization strategy. So this green triangle here, and approximate message passing is instead these techniques here. The other one is more machine learning, as far as I remember. And you see that expectation propagation is able to retrieve and say a better signal. So this is the error with respect to the true one. Okay. So very briefly, another application that we try is linked to the inverse problem in the EEG, where basically you want to retrieve the area of the brain that spikes where you collect some voltages from the scalp. Okay, so, and also in this case, the problem can be formalized as a compressed sensing problem, where the number of measurement that you have here is the number of electrodes that you put in the scalp. These J, let's say, are the currents, so, or let's say the activated area in the brain, and this number is NG. And this K matrix is called the kernel matrix that actually takes information of the spread of the electric field from the interior of your brain to the scalp, and this is somehow given. What we try to do is to also include some structure, let's say, of the areas of the brain, and to do that, we include some prior knowledge of this area into this, let's say, atlas. They are called Atlas A. And instead of imposing, let's say, this prior information about the currents into the unknown J, we decided to put this information into the sensing matrix K. Okay, so we have a new sensing matrix that takes into account this correlation. And in the end, this K matrix, it was very, very structured. So where the entries were ugly correlated. And these are, let's say, the areas that we tried. So this is, let's say, the so-called ring brain, so a two-dimensional version of the brain. Instead, this one is the plot of the areas in the three-dimensional brain instead. And these are, let's say, give you some results. So we, let's say, synthetically performed simulation where we activated, for instance, these three regions. We collected some voltages here synthetically, and this is the reconstruction. So the true signal is the blue one, instead the red one is the one achieved by expectation propagation, and this is the plot of the inferred currents. And you see that even though there are some errors in the position, let's say, of the spikes, the area are actually well retrieved. And we did the same when using the three-dimensional brain. So we activated synthetically these are three areas, even though these two are very close by. And we collect some voltages, and this is the result of the reconstruction. So the true one are the blue, and the red one are the ones provided by expectation propagation. And if you look at the plots, you see that there is a very good overlap between the two figures here. So these results are actually, so the ones about compressed sensing are all provided by this paper. Instead, this part about the inverse problem EEG is only present in my PhD thesis, unfortunately. Okay, so now what's, I think, yes, 10 minutes. So what's next? What we are doing now is to exploit the fact that we are able to deal with, let's say, this L0 regularization, and to apply this approximation scheme into, let's say, other different problems that go beyond the, let's say, compressed sensing. What I'm doing in this month is to try to use this approximation and train the retrieval machine. In the case of MNIST databases or maybe protein data, where you want to impose, let's say, this sparsity in maybe both visible but also hidden units of the retrieval machines. Another, let's say, application of this is a compressed sensing technique, where instead of the sensing metrics, you use for instance, the principal component base, and you want to use, let's say, only we want to compute this basis that is only made of the eigenvectors associated with the largest, for instance, k the largest k eigenvalues, and so you want to store the less possible data, so the less possible projection, and to retrieve exactly the original signal that in this case can be whatever data. And if this data is, let's say, sparse in the original space, for instance, you have a set of, say, the images that are kind of sparse, then if we add, let's say, this L0 regularization, you can get better reconstruction instead of using, let's say, the typical framework where you only let's say try to invert this linear relationship between the compressed data and the original data. Okay, so this is the end of my talk. This is, if you want, a list of the papers that I have been mentioned during this seminar, and I will be very happy to take questions if there are any. Thanks a lot.
Okay, thank you very much. Thank you very much, Anna Paola, for the talk. So, are there any questions? Okay, so I have one question. It is about, it was in slide 19.
Okay, thanks. You're very precise. Okay, this one?
Yes. So, okay, it's more like of philosophical question in a sense. So why do you choose to minimize the Kullback-Leibler divergence instead of, let's say, I don't know, Wasserstein distance or other kind of distances between these distributions? Yes.
It's a nice question. And the fact is that I think, but I can be wrong, that if you do this minimization analytically, you are able to say to close the equation in the sense that you get this matching in the end. And from these two equations, you can get, let's say, closed equation for A and B. Instead, if you use a different distance between probabilities, maybe you are not able to compute, let's say, first of all, the integral which is associated with this distance, and then to minimize it analytically. So in a sense, this is convenient from analytical point of view, but from let's say from a point of view of the quality of the results, maybe also using other distances can be useful. I never tried, but it's a good question. Yeah.
Okay, and maybe a second question related to this one is, okay, you mentioned that there is some, if I understand correctly, some criterion about convergence of these updated equations.
Yes.
So is there any theoretical reason to expect that this fixed point is unique, let's say, or?
It's not unique. Mm-hmm. Indeed, if you say from a statistical mechanics point of view, you let's say you can compute free energy, if you want, associated with the approximation. And if you try to minimize the free energies as we do in, say, statistical mechanics, you will see that actually there are other solutions other than this solution here. So this is a kind of a spatial solution, but there exists other in principle, if you only look at the free energy. And you can show that, so this solution is like kind of stable. So it means that if your parameters are able to satisfy these constraints, then also the more general one is satisfied. So it's okay, but there are also others. And actually, one PhD student actually tried, instead of using this scheme, to use the one that was like suggested from a free energy calculation, but the results were not very clear. So you are not sure actually there are also other minima. I don't know if any of the original researchers like Hopper or Winter tried to get some more intuition about the fixed point of this. Yeah.
So you have a criterion on the Asian to say that this one is.
In this scheme, what you do to get to say that you reach the convergence is just to compute, let's say, the absolute value of the difference between the two, or you can say, let's say, iteratively, what is the difference between the A of the B at t plus 1 and where t is the iteration and t, and then you stop at a certain point. Okay. Even though in this comprehensive problem, this is very easy. If you start from a certain initial condition for the parameters, you will end up with the same fixed point, starting from different initialization, let's say. Instead, what we are facing in the here in the restricted Boltzmann machine case, we are actually seeing a sort of breaking of the symmetry, if you want, of the solution space, because if you start from different initial condition, you will get different convergences. And so maybe this expectation propagation is actually seeing, let's say, it's convergent to local minima. And so actually here we are trying to get, let's say, more sophisticated approximation in the end, because otherwise we are not really able to do the training properly. But it's very, let's say, debated, if you want, these convergency issues.
Okay, thank you.
Welcome.
Are there any other questions?
There is some question in the chat, Matthew.
Let me.
So yeah, so I can read it if you wish.
Yeah. Okay.
So the question is, how are the results affected by a quantum property of the problem where any measurement alters the state of X?
I have no idea. No, I mean, this is, I don't think that this scheme has been used in, let's say, for quantum states. So I don't know. I really don't know. So this works for, let's say, continuous variables from this sense, but if you have, let's say, a wave function associated with this, I don't know how can we, sorry, I don't know any about the application of these techniques in quantum mechanics. I cannot answer.
Okay.
Okay.
So, any other questions?
It's not really a question, but I remember from my master's, I read a paper from Candice about the minimization of the rank of a matrices. And nuclear norm also. It's like a heuristic to the same problem, which is the rank of matrix. And I remember it's related to compressed sensing. So I am not sure if there is some link or to the problem. The problem we are working with. If it says something
maybe,
to you.
I think that there is kind of a link in the sense that if this matrix A, so this matrix A is made, let's say, of M equations, but you can think of this A as an original, let's say, N times M matrix, where instead it is maybe low rank. So basically, the number of independent equations that we have it would be equal to the number of the rank, let's say, of A. And so in the end, if you want to minimize the rank of this matrix, it's like asking yourself what is the minimum value, the minimum number of equations that you can have in this sensing matrix. So the minimum number of measurement in this context, such that I can retrieve the original signal. So this is, let's say, the only connection that I can see here.
Okay, thank you very much.
Welcome.
Just, some memories.
Okay.
Okay, so I have another question about, let's say, the end of the talk, around the slide 24 or 25. Yeah,
Okay.
so exactly, yeah. So I was wondering, I mean, how generic these results are. So, I mean, how many, let's say, data sets you considered? Are there any constraint, of course, on the choice, on the number of data sets and some development?
Yeah, I've never, I didn't, let's say, go into the details of this. It's like an initial study that we did during my PhD, and then unfortunately we did not go into the details, but in general will be very interesting. It's, let's say, what we tried, it was to, let's say, change these, let's say, kernel matrices. There are a lot that are present in literature, and the performances were kind of stable in this sense. So changing this K, then the retrieve of this J was actually sufficiently fine. And then also here you have two atlases, and I think that not many atlases existed for this problem. So let's say the 2-dimensional and 3-dimensional dictionary, okay, of the brain areas. And also here, if you start increasing the number of activated areas, then you get, for instance, the number of non-zeros in this comprehensive problem that maybe is too large. And so the problem becomes very, very difficult because you don't have much information. So you don't have a sufficient number of equations in this respect. And that's it. But the problem is that here, everything is very is synthetic. So what I do is what I did basically simulate this activated region in my laptop. There would be very much more interest to look, let's say, to get voltages from actual measurement from the scalp and compare maybe our prediction to the prediction that the machine, the hospital give you. Okay, that will be much more interesting. Then something that I didn't mention is that the running time of all this approximation scales as a cube of the number of variables, so the cube of n, because when you have to compute this matching of the moments, so basically the statistics associated with the multivariate Gaussian and the tilde distribution, you have to invert a matrix, and of course the cost of the inversion scales as a cubic of n. So if you have this n, which is very large, as you can imagine the number of reads that participate to the activation of areas in the brain, then it will be too slow to be, let's say, applicable in a let's say actual context. So let's say that in this regime we never we didn't go into the details of this computation. We did a little bit more in the context of tomographic images, but it's still an ongoing, let's say, project, and is slightly different with respect to complex sensing.
Okay, thank you very much.
Welcome, you're welcome.
So are there any other questions? Okay, if not, let's thank again the speaker.
Okay, thank
you
you
very much.
Thank you too.
For this nice and clear talk.
Thank you.
And I take this opportunity to remind that we are resuming in 2 weeks with the next talk of this series. Okay.
Okay.
So have a good afternoon, and thank you again for participating.
Okay, thank you very much.
Bye bye.
Thank you. Bye. Ciao, Matteo.
Thank you.
Ciao. Bye.
Ciao.